last time we discussed very briefly maps. And I cannot say much about it, but still something. And I will say something which maybe is not in my notes, and which maybe may seem reasonable for you that you know it. So first of all, definitions which are in my notes. We have two manifolds. Opa. We have two manifolds, as you can guess, x and y. Not of the same dimension, no relation between them. So x and y are manifolds. Then, in particular, these are two sets. So it is possible to speak of a map of x into y. Now I want to give a definition of a smooth map. First, I assume that it is continuous. It may be formulated in some other way, but this is the most frank condition. Continuous because x and y have topology coming from the smooth structure. Number two, if we have two charts of x and of y, then out of these two maps I can do the following, and I can take psi of v, I can take f minus f inverse of this, and then phi inverse of this. And this will be a map of a certain subset of u. This is not a map, this is a set. So the map actually is f. So we have a point P here, we take phi of P, we take f of this and psi inverse of this. And this is a point in V. This set is open simply because I assume that f is continuous and this is certainly also continuous. So this is a map between of an open set in Euclidean space into another open set in. So this is part of U. And this map can be smooth in the very usual sense of this. If this map is smooth for all charts, for pairs of charts, then the map is called smooth. Then some definitions which are not very interesting, but still. So there are smooth maps, which means C infinity. This map F may be invertible. And if it is invertible, then there is inverse map. And we can assume that it is also smooth. So if F is bijective, and both F and F inverse are smooth, then it is called a diffeomorphism. And it is, as in algebra, when we speak of isomorphisms of groups, if we have two manifolds which can be joined by a diffeomorphism, then they call diffeomorphic, like groups call isomorphic. And then, in some respects, they are the same, not distinguishable. Every property of the manifold X becomes a property of the manifold Y and vice versa. In particular, they have the same dimension. Otherwise, it cannot be invertible. So, diffeomorphisms. As I say, it is quite common that actually we consider manifolds up to diffeomorphism. But on the other hand, it is maybe not reasonable from a pure algebraic point of view. For example, if two manifolds are diffeomorphic, there may be many different diffeomorphisms between them. So if I know that two manifolds are diffeomorphic, then if I take a point in one of them, it will not correspond to any point in the other one unless the diffeomorphism is fixed. There are pairs of diffeomorphic manifolds, well known. Do you know some? Say RP1, a real projective line, is diffeomorphic to what? You know? To a manifold which you know much better than projective line. To a circle, yes. Very easy to understand. I will not explain this further. There are other diffeomorphisms. Some of them are sort of less visible. For example, SU2. You know what SU2 is? So we have matrices, complex matrices, 2 cross 2. U means they're unitary. If you know what it is, you can immediately explain. And S means that the determinant is equal to 1. So SU2. It is not hard to understand that this is diffeomorphic to, who knows? S3. SO3, the group of, by the way, why, let's take SO3. I say that this is a manifold. Why I say so? Why do I say so? Do I need to explain charts, everything? No. SO3 is a subset, yes, subset. In the set of all 3 cross 3 matrices, right? 9-dimensional space, which is a manifold. And it is described by certain conditions. Conditions are equations. Every row has the sum of squares of entries 1, and every 2 rows are orthogonal to each other. So there are 6 conditions. It is a check shows that the conditions are independent, and we have a 3-dimensional manifold in R9, and it is diffeomorphic to RP3. There is one more diffeomorphism, last one, which I will be mentioning. G plus 2, 2. First GMN, Grassmann manifolds. I explained some time ago what it is. So in the space dimension m plus n, we take m-dimensional subspaces. This is GMN. Real space, real subspaces. This plus, tiny plus after G means that I consider not just subspaces, but these spaces with orientation. Oriented planes in R4 form this manifold, G plus 2, 2. And this is diffeomorphic to S2 cross S2. Very interesting diffeomorphism. There are some other diffeomorphisms between classical manifolds of small dimensions. So this is one thing which I wanted to say. Then the second thing. Diffeomorphisms are diffeomorphisms. There are also maps which are called embeddings. Very easy to explain in our language. An embedding of one manifold into another manifold is a diffeomorphism. So an embedding of X into Y is a diffeomorphism between X and some submanifold of Y. Period. So X becomes not distinguishable not from Y, from a submanifold of Y. And we can say, I think, that this expression is natural, that X is embeddable into Y, that X is embeddable into Y. And here comes one very important theorem. In this form, actually, it is trivial. I will prove it eventually, but not today. That every manifold at all, no exceptions, can be embedded in Euclidean space. Then there exists a chain of theorems about the dimension of this Euclidean space. When I was a student, actually undergraduate, this was my favorite subject. So there exists a classical theorem which is called Whitney theorem, that every n-dimensional manifold is embeddable in R to n plus 1. There are similar theorems for complex manifolds, special complex manifolds in algebraic geometry. So there are some theorems of this kind, but in topology, it's one of the most famous theorems, that every n-dimensional manifold is embeddable in R to n plus 1. Actually, this theorem, there is a much stronger theorem. Whichever continuous map, let's be smooth map of a manifold of dimension n into R to n plus 1 or into R of some bigger dimension, you can approximate it in a very strong sense by embeddings. This is Whitney theorem, which proved in the 30s, and from the modern point of view, it is absolutely trivial. What if you want to reduce the dimension to n plus 1? And you know what? It's also always possible. There exists a theorem that every n-dimensional manifold, of positive dimension, and n is greater than 0, is embeddable into R to n. But no approximation now. You can check, you can guess it. Can you imagine a map of a circle into a plane? Your favorite figure 8, right? Gives you this map of a circle into the plane, but not one-to-one. It's not embedding. And it can be approximated by embeddings. But the embedding of a circle into the plane exists. Please don't say to me that you don't know that. If you don't know that, just take a compass. And what about embeddings in smaller dimensions, 10 minus 1? Not always possible. But there are very funny theorems. For example, if your manifold has dimension which is not the power of 2, not 2, not 4, not 8, then it is embeddable into R to n minus 1. Or even if the dimension is a power of 2, but the manifold is orientable. Again, this is embeddable into R to n minus 1. So many theorems. Actually, there exists many theorems in topology about embeddings which estimate the dimension of a space into which the given manifold can be embedded. And I cannot say that it is immensely interesting, but maybe I'm not in position to say this because I was very much fond of it many years ago. So this is one thing. And now I want to discuss with a very serious subject. When we give definitions, and this is a stupid question, why is this definition and not other definition? But still, sometimes such questions arise. Why C infinity? Why do we choose C infinity and not anything else? It is very clear that our definitions can be repeated without any serious changes within many other classes of smoothness. Do you know what CR means? CR means R continuous derivatives. Continuous derivatives up to order R. Then there is C0, just continuous maps. Then, if we know to the higher level analysis, there are analytic maps. In the complex analysis, holomorphic maps and everything. The same Whitney, actually, I didn't say this, right? The embedding theorem in R10 also belongs to Whitney. Actually, the theory of manifolds as it exists was developed by Whitney in the 30s and the 40s, Husser Whitney, many different senses. But again, there exists, from the point of topology, no difference between C1 manifolds and C infinity manifolds and everything between. If we have a CR manifold, and R is a positive integer, then theorem 1. I will prove it, but usual standard approximation theorems which exist in analysis give you an immediate proof. So you have a CR manifold. Proposition 1. There exists a C infinity manifold which is CR diffeomorphic to this manifold. So this CR structure can be improved to C infinity structure, and in a unique way, in the sense that if we have two different C infinity manifolds, CR diffeomorphic to our CR manifolds, then well, it is obvious. Then they are CR diffeomorphic to each other. There is a slight difference, an important difference, between the smoothness case, between C1 and C infinity, and the two extreme cases, C0 and analytic. C0, the theory of C0 manifolds is something very special, and absolutely we are not able to touch it in this course of differential topology. C0 manifold is not a space with a structure. Simply can be described as a topological space, so that every point has a neighborhood homeomorphic to an open subset of Rn, or to Rn. It is a definition of topological manifold, C0 manifold. Now, do you think it is true that every topological manifold is homeomorphic, what else, to a smooth manifold? No. No. There are many topological, Yasman, you know this. There are many topological manifolds starting with dimension 4. In dimension 3, it's impossible. Starting with dimension 4, many topological manifolds which are not homeomorphic to any smooth manifolds. So this is one extreme case. Another extreme case is an analytic case. Here the situation is different. You see, all we can prove about C infinity manifolds is true for analytic manifolds. Any any smooth manifold has a unique real analytic structure. It is true. The difference is that the proofs are different. And it was not Whitney who proved it. It is, how to say, at least as far as I know, it is a complicated theorem using a high-level analysis that, yes, every smooth manifold has an analytic structure. Actually, even real algebraic structure. It is another theorem. For analytic manifold, the proof was given in the 60s independently by Malgrange and Grauert. Grauert was a big expert in complex analysis, so it actually proved, as it often happens in mathematics, by using complex tools. Malgrange, no, this proof, which I understand very well, the proof of Grauert, not so well the proof of Malgrange. That one was analytic. Malgrange was an expert in PDE. As to the algebraic case, it was this theorem in slightly weaker form was proved by an Italian topologist, Tagnoli, and in this final form by John Nash, whom you know maybe from the movie and maybe from some other sources, but also a wonderful mathematician. I think this is all what I can say about embeddings, and now simply I want to introduce one more word. This word is immersion. an immersion is a smooth map of x into y, such that for every point x in x, there exists a neighborhood, such that this is an embedding. So if you want to describe it in a short sentence, you can say that immersion is a local embedding. This is an immersion. Of a circle into the plane. You see that certainly it is not an embedding, but still locally it is an embedding. So if you take a small piece of the circle sufficiently small, then restricted to this map will be an embedding, right? So this is an immersion. This definition of immersion technically is not very convenient, and we will have a different definition. But now I want to stop here with these words regarding embeddings, immersions, and so on. So questions? Questions?
I have a question on something a while back. I have a question on something a while back, which is you mentioned that for your definition of smooth maps between manifolds.
Yes, something wrong with this. Oh.
Chairs over here.
Thank you. Thank you. I have it.
Why that condition of continuity is separately required when you already have the maps are smooth when you go from coordinate patches?
I don't quite understand, but I don't know what to say. We have the notion of smoothness for Euclidean spaces. A map of an open set in Euclidean space, in general Euclidean space, is actually determined by coordinate functions. So a map of an open set in Rn nic into Rm mic is just m functions on U. And I know what it means that they are smooth, just they have continuous derivatives. So what's the question?
So when you describe smooth, when you define smooth maps between two manifolds,
Yes.
you required that the maps are continuous separately.
I simply want that this is open. I can say this is open as a cell. And then continuity will follow from this. You see, the notion of a smooth map for Euclidean spaces is defined for functions given on open sets. Derivatives, require that the function is defined around a point. Certainly, I can, if you prefer that they do not use the word continuous and say that smooth maps are continuous by definition, then I need to replace this condition of continuity by the condition that this map is smooth, this thing is smooth. But the inverse image of smooth of open set is open. It is more or less the same. So this condition of openness of the set is equivalent to continuity. Continuity is simply one word instead of several lines. This is what I prefer. But certainly, and I believe that maybe in reasonable texts in differential topology, continuity is not required. It requires something equivalent to it. I just wanted to be more frank. Okay. Now, the next thing, smoothness. There are smooth maps. There are best maps in the universe, functions. So there are smooth functions. Again, a very interesting thing. If you have a manifold, then some functions, manifold is a set, but there are functions of the set with values in real numbers. And they can be smooth. They can be C infinity. C infinity is what we actually want, and we have the set of all C infinity functions on a manifold as a set. It is not a set. It is a vector space. It is actually an algebra because you can multiply them. It is an algebra. An algebra, real algebra of functions. It is usually denoted by C infinity of m. You know, there exists an approach not only to manifolds. Very common in mathematics. I believe that the idea belongs to Grothendieck. Instead of considering different geometric objects like manifolds, varieties, what else, you consider actually functions on them. In algebraic geometry, it's very common. Take an algebraic geometer, which is more algebraic than geometer, and ask him what an algebraic manifold is. And you know what this guy will say? He will say, it is a ring. Why a ring? An algebra. It is an algebra. Because for him, a manifold is actually algebra functions. What are points? Points, he will say, are maximal ideals. What are submanifolds? Ideals. And so on and so on. Whatever you have in differential topology can be repeated in algebraic geometry simply by replacing geometric terms by algebraic terms. And sometimes it is important, for example, if you consider algebraic geometry over a finite field or something like this, then certainly geometry disappears. But algebra is still there, and topological notions like homology and everything exist for algebraic manifolds over, say, fields of finite characteristic, because you can consider rings of functions. There is a theory in differential topology, proved in the 60s by Schultz, that if for two manifolds their algebras C infinity are I of functions, are isomorphic, and that's all, just isomorphic, as algebras. Forget topology, forget everything. Just two algebras isomorphic, then the manifolds are diffeomorphic. So in some sense, continuous smooth functions on a manifold create a theory similar to the theory of manifolds. And it is possible actually to consider something similar to differential topology taken for the main object, not a manifold, but a ring. Unlike algebraic geometry, differential topology is resistant to this, and the theory is not equivalent to differential topology. These rings may be very different from rings of functions on manifolds. Still, all the notions exist. Notions which we already have, and notions which we will have eventually. Yes. I just wanted to mention it. And now let us turn to the functions. I want to mention just several constructions in analysis, which are used in topology and which are known to you, I believe, better than to me. So I want to mention several functions just of real variable. E to the power negative x squared. The favorite example of all instructors in analysis. Why this function is remarkable or so ugly? This is because at this point, excuse me, I didn't say this. It is minus x squared if x, and 0 if x is positive, and 0 if x is negative. Yes. This function is remarkable or ugly because at 0 all derivatives are equal to 0. It is very close to 0 as 0. All derivatives are 0. Nevertheless, So the Taylor series of this function at 0 is 0, completely 0. Still, this function is not 0. People say that it's not analytic. Well, I don't mind. So this is number 1. I believe this in my notes. All these functions have notations, and probably I better follow these notations. So let me take a copy of my notes. Yes, this function in my notes is called not f of x, but rho of x. The next one. Take 2 points, A and B, not necessarily positive. 2 arbitrary numbers, A is less than B. Then there exists a function of this kind. It is positive between A and B. It is 0 outside the interval AB. And it is C infinity. That is, again, all the derivatives of these 2 points are zeros. It is, according to my notes, sigma AB of x, and the best definition is just take rho of x minus A times rho of B minus x. Between A and B, this is positive. But between A and B, A minus x and B, x minus A and B minus x are both positive. So a function like this. Then you can take the integral of this function again A and B, and you can get a function like this, which is 0 here, 1 here, and C infinity, and between 0 and 1 the interval AB. This again is an infinity function. The best way to define it, it is called tau, right? Yes, tau AB of x. Take the integral from A to x, sigma AB of x dx, and just to make it 1 here, not any number, you divide it over the interval of A to B. Divide over this area. So these are the 3 functions which we will need. Mostly that one, but I don't mind all of them. Okay? Now a function of n variables. Take this tau r. We have 2 numbers, 2 positive numbers, small r and big R, and small r naturally less than big R. And I define this simply as tau lambda. Now I hold the head. Tau r. You know, with these definitions, I better say 1 minus tau r. 1 minus tau r of the radius. So this function is equal to 1 at 0, is equal to 1 at a small disk around 0, and is equal to 0 outside a bigger disk. So these 3 funny notations. these three finite notations. Now, out of these three very finite notations, I want to deduce still more funny result. Two of them actually. No, three of them actually, according to my notes. You know, you can say that we do not care of functions of real variables. We care about manifolds. Okay, I don't mind. But even for manifolds, we can create something using this construction. Actually, I will use that one. We have a manifold X. We have some point. We have some neighborhood of this point. Now I want to say that there exists a function, smooth, very smooth function, which is 1 in some neighborhood of X, and which is 0 in the complement of the neighborhood of X given from the beginning. These functions can be constructed from this immediately using local coordinates. I don't know whether I need to say anything about this. We take a chart which is contained in U, say that X is the image of the origin, and say that the image of a big disk, radius R, capital R, will be inside U. Then the same function will give you what I said. So a function on X, 0 everywhere in the complement of U, it's an infinity function. And all the values of this function are between 0 and 1. And the function is 1 at the given point, and also within some neighborhood of this point. What about that? What about that? Buy it? Because if you buy this, I will try to sell something less obvious, but still very important. So what I say, that there exists a function. I can forget the construction. For every point in the manifold, there exists a function which is equal to 1 in the neighborhood of this point, which is between 0 and 1 everywhere, and which is 0 in the complement of a chosen an arbitrarily chosen neighborhood of this point. If you buy this, then you will have to buy something less obvious. You ready? Suppose that you have not just a point. Who cares of points? You have a manifold X, and you have a compact subset of X. Do you know why I denote it by K? Very strange. Compact subset. Why do I denote it by K? Because that's what compact. You can say that it is written with C, not with K, but it is a German word. It is a German word. Do you know how an open set is usually denoted? In analysis everywhere. What is the most? U. Why? Why U? Again, German word, Umgebung. Closed set. How is this denoted normally? Maybe it's less common, but still, usually F. But this is a French word, fermé. German word abgeschlossen will not give you a good abbreviation. You know, this topological terminology was not created by English-speaking mathematicians. And by this reason, many notations come from different languages. Say, if you see that a vector space is, or not the space, is denoted by E. This is French espace. Well, it is not a lesson in foreign languages, so forget about it. So let K be a compact set. Also U, if you like this. Is a neighborhood, which simply means an open set which contains K. Now I want to create a function f, smooth function, x into R, which is 1 on K, 0 on U in the complement of U, and taking values between 0 and 1 everywhere. Do you have any idea how to create this function out of the material which we have? Because we don't have any other material. You have an idea?
Cover it with small sets.
I think covering will, I don't know what to say. Just let me say this in proper words. You can say that for every point of K, to every point of K, we can apply this construction. And to the same U. So for every point of K, we will have a function which is 1 in the neighborhood of this point, and 0 outside of U. Then you want to use compactness, right? Use compactness means that you say that these sets where functions are equal to 1, they cover K. And we can find a subcover, because this is the definition of compactness. Very interesting. What next? So we have finitely many functions. We have what? Now, according to your construction, which I accept, we have functions f I, x in R, and every fi, this is K, is 1 in the some neighborhood. I can denote this, say, Vi, and 0 in the complement of U. And now this actually, we can assume that this sets Vi cover K, and there are finitely many of them. I What next? What to do next? What's your suggestion? Here, I believe you want to say that we can take the sum of these functions. It will be okay, but not quite okay. It will be 0, certainly outside of U. It will be positive on K. At least 1 at every point of K, but not 1. It may be on K, this function may be not just 1, just some at every value in K will be, well, positive and at least 1. It is true. This is true, but not 1. Certainly for all applications it's sufficient. But if you want to have this function equal to 1, then it is better to write now that f is 1 minus the product of 1 minus fi see that this will work, because first the value of the function is 1 minus something. Something is at most 1, because it's a product of numbers less than or equal to 1 and positive. Well, no negative, yes, no negative. So this function, it is 1 on K, because at every point of K, sum fi is 1. And 1 minus 1 is 0, as you may know. And if a product contains 0, then it is 0. So this strange expression satisfies all my conditions. And then I believe this is also, I have 3 more minutes, and what I'm going to say maybe can be said in 2 minutes, maybe even 1. Some topological property of important topological property of a manifold comes from this. So forget the functions. Forget the functions. Suppose that we have a compact set or a point actually, and some neighborhood U. I want to say that there exists a neighborhood V of the same set, such that the closure of V is contained in U, and V contains K. So this compact set can be separated from its complement by a function, by in this way. If K is a point, then this property is in point set topology is called regularity. So for every point and every neighborhood of this point, there is a smaller neighborhood of the same point which is contained in our neighborhood with the closure. By the way, some quite interesting topological space don't have this property. This property, Hausdorffness, is more common. It is stronger than Hausdorffness. Because here we separate actually, in some sense, we separate a point from every closed set. What is complement to U? A complement to U is some closed set, arbitrary. So we can formulate in such a way that if we have a point and a closed set, then there exists a neighborhood of this point whose closure is disjoint from this closed set. This property is called regularity. Actually, there exists a stronger property which is called normality. The same for 2 disjoint closed sets. Two disjoint closed sets have neighborhoods whose closures are disjoint. It is a strong property which manifolds also have. But at this moment, we have this. This is contained in our period proposition, because if we have a compact set, K, we have K and U, then we have this function f x into R with the properties which are listed, and then just take V equal to f those x, f of x is greater than 1/2. This will be an open set. This will be its closure if the set where f is greater than or equal to 1/2 at least is contained in it. So the closure is contained in U, and certainly contains K. V contains K. So this regularity property follows from this. At this moment, I finish the subject. I finish with functions and manifolds. We will consider different things. Again, topology, equally boring next time. Then it will be something more interesting. Maybe my next lecture, if you come, will be something more interesting. We will consider vector fields, tangent vectors. This is something really interesting. And next time we will consider open covers and their properties of manifolds. I think this is all. Yes.